about you, but like I feel so inspired. I feel excited, enthused. I don't even know what to say in regards to descriptive, because it's been great. It's been such an amazing day. So before I introduce our next speaker, I'm going to be fangirling a little bit here, so just bear with me, okay? We have Dr. Rebecca Pope, is a clinical neuroscientist and director of data science and engineering from KPMG UK. Rebecca is responsible for leading an expert team of data scientists and engineers to build scalable, high-performing data science and artificially intelligent products to transform and drive business value for KPMG's global client base. Rebecca's industry focus is the ethical application of AI to improve mental health and social care for all. Yes, I'm always going to be snapping my fingers at that, Rebecca. Thank you. She was voted as the most influential woman in UK tech and is on voluntary secondment 1 day a week as Great Ormond Street Hospital's data science strategy lead. Dr. Pope, I have one thing to say. Hail Queen. Hail Queen all the way. I'm going to hand it over to you.
Oh, it's absolutely lovely to be here. Can I just make sure that you can hear me okay and see me okay before
yes, we can
start? Fabulous. So firstly, wonderful to meet you all wherever you happen to be. I hope I find you kind of safe and well, and your families are well. I'd like to just give a massive shout out as well to all the people that have organised today and the event. I've worked really closely with Chloe and Adam, who realised last night how poor data scientists are at actually using any type of online platform that isn't Microsoft Teams. So without further ado, I'm just going to share my screen and get into please let me know when you can see my screen, and then that would be super, because I can't see you. So I need some wonderful person in the conference to come off mute and say, can you see Demystifying AI on your screen before I kick off? Otherwise, I'm going to have to break into Lionel Richie and start going, hello.
Rebecca, I can't see anything from there.
You can't see
empty, so I'm just seeing there.
Okay, maybe because I haven't hit share. There we go. Just keeping the music theme alive. Can you see it now?
Yes, and I definitely would have been your backup there for you singing the Lionel Richie, so I'm just going to have to fade in the back now.
It's a classic. Can I just make sure you're seeing the right screen as well? You're only seeing the one.
Demystifying artificial intelligence.
Yeah. Fab. We're there. We did it. Wonderful. So yes, demystifying artificial intelligence. I think it's really important to start actually with what artificial intelligence is not. If you have this idea of artificial intelligence in your mind, the killer robots, the kind of idea of conscious beings, please erase it from your mind. Okay, that comes about because of the way the media anthropomorphize or try and humanize this technology. It absolutely isn't that. So that then leads to the question, well, if artificial intelligence isn't this, then what is it? Well, essentially, it is a software Swiss Army knife tool. And I don't know about your night last night, but hopefully you didn't open your bottle of wine with a pair of scissors. You used a corkscrew, for example. And what I'm trying to get at here is that artificially intelligent systems are narrowly intelligent in their application. Okay, so you can't and shouldn't use one type of system, maybe a system that you've trained to play chess, to then go and make a cup of tea. Okay, that's not how this works. But there seems to be this general thought that an AI system can do everything because we've put Jazz Hands AI in front of it. That isn't the case. Okay, they're narrowly intelligent. We haven't reached the point of what we call the singularity or generalized or intelligence yet. Now, I'm really aware, and I'm aware when I speak with my clients, that there are so many terms in this field. There's artificial intelligence, there's machine learning, there's deep learning, there's neural networks. What does it all mean? And I think this, and I borrowed this from Microsoft. I'll put the sources in there, sorry, the hyperlink. I think this is a really nice way of kind of thinking about artificial intelligence conceptually as like a Russian doll. So you've got your superset, which is artificial intelligence. And as it says here, that's any software technique that enables computers to mimic, and I'm going to come back to why mimic is so important, human intelligence. And it includes machine learning. So machine learning is really what people are talking about when they talk about AI, particularly, I think, in industry. So what is AI? Well, it's a subset. So we've taken the first Russian doll off. Next one is it's a subset of AI that includes techniques that enables computers to improve at tasks with experience. And maybe you think, well, my computer doesn't go and walk around the world. Like, what do I mean by experience? And what I mean by experience is computers have a huge amount of data. They can collect data about the world, and that becomes what we call a training set. And I'll get into that a bit later. But that's what we mean by experience. Now, if we take the next part of the Russian doll, you're then down to, well, a subset of machine learning includes deep learning. And I would put a good amount of money on the fact that you have used deep learning probably in every single day of your life for the last 3 years. Now, deep learning, as esoteric as that may sound, is what are the kinds of technologies that fuel Google, Netflix, Amazon, any kind of financial transaction system that is looking for abnormalities or financial crime. And that's really a subset of machine learning techniques based on what we call neural networks. And hopefully by the end of today, you'll have neural networks down. You'll be like, I know what a neural network is. That was so 2020. But what that neural network does is it permits a machine, a computer, to train itself to perform a task. And that's fundamentally different approach to training machines or computers. And we'll get on to what that means in a little bit later. So what is machine learning? Well, we've just covered that. It enables computers to learn and find patterns in a set of data. And traditionally, actually, what we do as data scientists is we don't just take one set of data, but we take a whole array of data sets. So that might be different types of Twitter feed data, it might be transport data, it might be COVID-19 type data. We try and understand and make a narrative, and that's really the art of data science. It's the ability to use a whole array of different data sets to enrich and understand about the world ahead of us. So how is that different from maybe what we would consider as traditional computing or traditional programming? So typically, traditional programming question to ask, like when you go to the doctor, for example, or to a hospital, when you're sorry, I'm much better at Python than I am PowerPoint. Okay. When you see a doctor, they will make notes about you, and then those notes that are captured will go to the wonderful people in medical records, and they will translate those notes into clinical codes about your care. And those codes are called Icd-10 codes, okay? They're called labels. And so in traditional programming, for example, I'm diabetic. So if I go and see my doctor, they will put diabetic, and then somebody in medical coding will have to sit down and go, right, diabetic equals this code. Oh, and Rebecca also has these other comorbidities. So I need to put these other labels with her electronic healthcare record, okay? Now, if you do that in handcrafted rules ways, every time somebody sees a condition, for example, in traditional programming, what you're doing here is you're having a nested if then else statement. You're saying if condition, the thing, contains the term COVID-19, then label it as this. If the condition contains something else, label it like that. And you can probably see from the way I'm speaking and my hand gestures that becomes a really, really long and handcrafted list that doesn't learn from experience. You constantly and manually have to update that particular list. And that's really kind of traditional programming. So how is machine learning programming different? Well, rather than telling the system what to do, so if condition contains this, then label this, you actually say, I want you to achieve the following objective, which is labeling condition. So just to bring that to life a little bit, in your code, or what you're really trying to do is not say how to do something, but what to do. You let the system kind of determine for itself how to do the task. So try to classify condition, change self to reduce errors, repeat, and you just keep reiterating through. Now that probably and doesn't mean very much to you, but I hope by the end of today, and this is hold me to account, it should make more sense. So as you heard, I'm a clinical neuroscientist by training, and I think it's really important to highlight that artificial intelligence is not the same as human intelligence. Artificial intelligence and all the techniques that sit under that superset of software tooling is biologically inspired. So this is the bit where I've been talking for about 8 minutes, so I'm going to ask you for some help. So I need you to either come off mute or put in the chat, because we have a very challenging task coming up. I would like you to tell me what animal you see in this picture. And I can't see the chat, so I need somebody on the wonderful organisation team just to read out what people are putting. And this is a litmus test of how much wine maybe you had last night. But what can you see on my slide?
I'm getting here, Rebecca, I'm just going to read them off for you. I'm getting here, definitely a cat, a house, a cow, fish, dog, and then somebody says, I'm just joking, it's a dog.
Hey. So wonderful. I particularly enjoyed the fish. That was awesome. So yes, it is a dog, right? Okay, now let's ask an AI system that I looked at a little bit earlier. So can you still see my screen? I just need someone to talk to me. Great. So what I've done here is Tensorflow is basically an end-to-end open source technology released by Google for doing something called deep learning. Remember, we've got AI, we've got machine learning, and then we've got deep learning. Okay, and that's where the architecture in itself, and we're going to come to that, is able to extract features from the data and train itself. So let's see that in action. So here all we're doing, and this is a Python notebook, is using that as a framework. We're saying go and get a particular image from a particular API, and I want you to go and, no one actually said Labrador, which I was a bit gutted about because I thought someone would be super specific, but go and get me the Labrador from this particular load of data that is freely available. And then what I want you to do is then I'm going to take what's called a pre-trained model. Okay, so I'm basically saying put this particular picture that you've just seen of someone called it a fish, but it is a Labrador, I promise. Put that and ask the system that's pre-trained on a whole load of images. Ask it what it is. What does it predict it can see in the image? Okay, and when I say see, what I really mean is classify. Okay, because these systems don't see. That's what our beautiful visual system allows humans to do. And what you can see here is just that image. Okay, and then what we're going to do is we're going to then start to add a bit of noise to this image. Okay, and we do that by, and this is a lot of noise, don't worry, but what we're going to do is like increase the amount of noise, and we just call noise kind of this adversarial pattern. We're just going to apply a little bit of noise to this image and see what the deep learning system that's been pre-trained thinks it sees. How confident is it in its prediction as well? And we're going to do that by this posh term, which data scientists use, but basically means noise. But if we say epsilons, it makes us sound really smart, but it is essentially noise, where we're going to say we're not going to add any noise, so 0 noise, which is this one. We're then going to add a little bit of noise, but not too much. Then we're going to increase that by a factor of 10, and then we're going to increase it a little bit more. And what we need to look at is how confident the deep learning system is in classifying the image, okay? And what it thinks it is will be at the top of the image. So remember, we started with no noise, and it said, yeah, I think this is a Labrador Retriever, and I'm about 40% confident. Okay, so now remember, we're going to add that 0.01% epsilon, that little bit of noise. Can I just ask you to tell me what you see in the image? So do you still see a fish? Please put it in the chat and read it out to me.
I think our fish person is gone, Rebecca. No.
Okay, what are people seeing in this image, in this second image? If you're still with me.
People are saying the same dog. Someone said
exactly the same dog, but what the system sees and is classified is this type of dog.
Okay.
And you can see, which doesn't make the whole big reveal very, but it thinks it now sees this, just from that tiny bit of change in the image. Okay, so it's now saying, actually, I think I'm seeing this. You didn't think that as a human being. Okay, so let's add a little bit more noise, right? Remember, this epsilon is what's going up. Okay, and see what the system says. Do you still see a dog? Yes or no? People, I need some feedback. Yes or no? Do you still see a dog? Yeah. Do you still see a Labrador?
Yeah. They're saying yes.
Okay, that's not what the system. Hey, that's not what the system is seeing. Okay, or classifying the image as. It's now classifying the image, now that we've increased that little bit of noise on the image, to this dog. And that's my point. These systems are not the same as human intelligence. None of you, I hope, joking aside with the fish, which I absolutely loved, joking aside, none of you would have, I hope, said you saw a completely different type of dog or completely different type of dog if you knew dog types, right? I do, because I just got a puppy and I love dogs. But the system did, okay? And that's what's really important. And maybe you're thinking, well, do you know what? Maybe actually Rebecca just didn't do a very good job in her coding. Maybe she got a really poorly trained, pre-trained algorithm to apply to the image. Maybe it's that, and actually it's not. So quite recently, it was found that a very well-trained system that saw a taxi classified it as a dog by 1 pixel change. That's 1 dot in the image. Now, just to bring that home a little bit, these are the kinds of technologies that underpin a huge amount of what we do in our daily lives. And I don't just mean the kind of Netflix and the Amazon. I also mean what underlies banking systems, what underlies financial crime and fraud. Deep learning is integrated into the fabric of our society, and invisibly so. So just bear that in mind when you can see actually how easy it is to trick these systems. But does that mean that these systems just aren't any good? Well, we're now getting into this question. Lots of researchers are suggesting, well, what are the limits of deep learning? Because we hear a lot of hype. It's going to take all our jobs. You know, we're going to have to, and I think there is going to be significant retraining because of lifelong training. But actually, we've seen that these technologies are limited. And Professor Geoffrey Hinton, who similarly has a background in clinical neuroscience, and you'll find a lot of psychologists, because they're trying to understand human intelligence, often like me end up in artificial intelligence, because you're trying to understand one by modeling the other. And he said something really interesting, and what you just saw was actually called an adversarial attack. It's again, it's data scientists trying to sound cool, but basically we're trying to say, if we add some noise or we trick the system, how easy can we start to extract mistakes, because that will tell us if we are really modeling human intelligence. And I think this is a wonderful quote. So this gentleman in 1986 released an amazing paper. I was 1 year old, I'll let you do the maths, where he started to speak about deep learning, and we're going to talk about backpropagation in a moment. But he said, I initially thought that adversarial examples like the one you just saw were just an annoyance, but now I think they're probably quite profound. They tell us that we are doing something wrong. Now, remember I said earlier that artificial intelligence really started as an academic, and continues to be a very academic field, to understand human intelligence. And I want us to kind of think about what is deep learning. And the building blocks of deep learning are what we call artificial neurons. So I'm going to do a kind of, hopefully, a bit of a 101 biology lesson here. But I want to show you that and demystify a lot of what this technology is doing. Okay, it's not to say that, you know, I did biology A level, right? That's not the purpose of this. So the building block of the human brain is the human brain's neurons, of which you have in the trillions of. Okay, and essentially what happens is, and I don't know whether you can see my pointer, but starting on the left hand side at the top, you get electrical chemical information that enters dendrites. Okay, so they carry the message, and that message is basically all the different messages coming in from all different cells are almost added up, they're summed up. And then if you get to a particular level of excitation, so you hit a threshold, the neuron will fire. Okay, and that neuron firing comes from the cell body. It's carried down the axon in electrical chemical signal, and it goes to the synapse, which basically then connects to other dendrites in the next neuron, and so we carry on. But this happens in a order of magnitude that is well, huge. It's not exponential, so that's why I stopped. So that's the biological system. How are we modeling that in artificial intelligence? So hopefully what you can see just from the image is that they look quite similar, right? So just like in the human brain, in deep learning, what we're trying to do, and why it's biologically inspired, is we say, well, let's model dendrites as inputs, right? So this relates to this section, right? All that you see around here. Then let's take the signal that is in each input and put it into a cell body, which, as you can see above, right? Now let's add up all the input signal and see whether it surpasses a particular threshold. And we call that an activation function. And as you can see, that's a non-linear activation function, right? It gets to a certain point and then it fires. It's not a straight line, okay? And then you get an output. So that's basically the building block of the human brain and also artificially intelligent systems, right? But how do we scale? What does that really look like? And what I want to do here is kind of bring that to life with some mathematics, and hopefully show you that it's actually relatively simple when you know what the symbols mean, because as long as you conceptually understand what you're seeing here, then you're more than halfway there to understanding what's happening in these systems. Okay, so don't be put off by this next section. So all I've done here is taken basically a very similar schematic, and I want us just to focus on section A here. So here again, these are our dendrites, our inputs, okay? And each input, X, and you have X1, X2, X to the N, because you have normally millions of these inputs, okay, is associated with a weight. So X1 is associated with weight 1, X2 to weight 2, and so on, okay? And this then passes, this is then all the weights times all the inputs, okay, is then basically summed. And that sum, remember this is the cell body, is then passed through and that's what's showing in the F here, a nonlinear activation function. And what that's doing is it's transforming that pre-activation level of the neuron that came in from the dendrites, that was added up, went through an activation function, and then it fires out to an output. Okay, so if it hits a particular threshold, you then get an output, which in this case is represented by YJ. So then if we take that into the system level, remember you have billions of these neurons in deep learning networks. You have what we call, so we're going to move now down to B, and this is an example of what we call a feed-forward neural network. And it's also referred to as a multi-layer perceptron, but it's basically a type of deep learning. And you have these input layers, remember, exactly the same conceptually as what's going on up here. You have an input layer, it's times by a weight, okay? And then what then happens is the addition of all the input times the weights is passed through the F, which is a nonlinear function, activation function, to give you an output of YJ. Then YJ, which is the output of the first hidden layer, is then passed through and serves as the input to the second hidden layer, represented by K. And you have exactly the same system that goes through these layers. And neural networks normally have in the hundreds of thousands of hidden layers, okay? But that's what's happening. You're having a signal pass through a system. And then eventually it will get to what's called an output layer. And what's happening here is exactly the same thing, but the function is slightly different. It's called a softmax function. And then you have a prediction, okay? So I have an input, which is an image, as I showed you earlier. So this is exactly what your visual cortex, at the back of your brain is, well, it's not exactly, but the model that we're making of the visual cortex is doing. You saw an image, you worked that kind of electrical chemical signal went through different parts of your brain, and then you eventually said that's a fish or that's a dog. Okay, so that's what's happening in artificial intelligence. So I said earlier, kind of, well, why is it deep? Okay, and I just want to bring this to life a little bit here. So let's say you've got an input image, and I didn't know until I read this paper actually who this was, but it's George Washington. And you've got input layers. What's the first thing the input layer does? Well, it essentially looks for light and dark pixel values. So it just goes through the image and goes, because dark and light basically have different numbers to show the computer that it's dark or light. Okay, so it works through this kind of matrix of numbers and goes, that's a high number, so it's dark, that's a light number, so it's low, so it must be light. So that's the first thing the input layer does. And then the next layer will go, well, let's start in the image to identify edges. And then it will identify combinations of images. And what you can see here is that the nose and the eye is starting to be formed. And then, as I said earlier, you identify features. And then you combine those features and you then say, of the combinations and of the types of images I could pick, which one do I think this input picture is? And the output here is George, for George Washington. And that all sounds fine, but we know that these systems don't always get it right, and they certainly don't get it right first time. Okay, and part of a data scientist role is actually teaching systems. I joke with my team that we are actually we teach computers. That is our job. So what if it comes out and says, this is Donald, and it's completely wrong, right? What do you do? How do you train the system and indicate to the system that it's wrong? Just like, how do you tell a child when a child sees a cat and says dog? Right, how you do it by actually saying, no, that's not a dog, it's a cat because of these reasons. And you do the same kind of thing with artificial intelligence systems. And how do we do that? Well, that is, remember this chap again, Professor Geoffrey Hinton, he introduced the idea of propagation. Okay, backpropagation is a machine learning algorithm in supervised learning. And I'm going to take you through what it does very briefly. So remember, we've got an input and we call it a vector, but that just means it's numbers. We've got an input, and you take your input vector in this case, and as you go forwards through this multi-layer neural network, remember with those non-linear activation functions, you end up with an output. And what you do with the output, remember in our case it said Donald, and we know that's not right because it's George Washington, that was the input. What you do is you then back propagate this error signal. You say you actually calculate derivatives of how far are you from what we want versus what you predicted, right? And that gap is your derivative. And that's the signal we learn, that the system uses to learn to correctly classify an image. Now, this is my call to action to you. So I got into artificial intelligence because I just found this whole thing about how we can model human intelligence really interesting, and came across deep learning. And as I said, this was kind of back in the early 1980s. It was kind of thought not the right idea because it wasn't biologically plausible, it wasn't fast enough. And it's still hotly debated. But what I love about, well, many things about Professor Geoffrey Hinton, but particularly this, because I think for somebody who has specialized in deep learning, so basically made, or was one of the main people to make Google as successful as it is, he said this wonderfully humble, I think, quote, and I think it's really a call to action to all of you sitting there today that are going through your undergraduate, your postgraduate studies, which is my view on back propagation. This is to throw it all away and start again. The future depends on some graduate student who is deeply suspicious of everything I have said. And I think that's wonderful. So my advice is always to be deeply suspicious, because I think that's what education, the point of what you're doing is to push boundaries. It's not just to accept what you're always reading. And I think that's the wonderful thing about research. So I just wanted to end, just not in a narcissistic way, but just very briefly talking about my data science career, because it certainly didn't start as a physicist or someone who created a computer age 2. People often think this, they think it's a very linear, you just worked your way up and that's how it's gone. No, that's not the case. And I think that anyone that says that their data science career is like that is not telling the truth. Actually, this is what my data science career looks like. I've worked at different organizations, I've done lots of different things, and kind of just like gradient descent, that's an in-joke, but hopefully some people got it, ended up as a data scientist. But it was never like, I'm going to be a data scientist, right? It's just where I've ended up and what I love doing. So turning to what do I need to do or be as a data scientist, my first piece of advice would be, don't worry about what you are learning. Worry about and think about, do I have the aptitude to learn and problem solve? Because that, in its absolute core, is what you need as a data scientist. The fact that you haven't done any Python programming, the fact that you don't know multilinear statistics at the moment, it doesn't matter. You can learn that, right? What fundamentally matters is your aptitude to learn, right? I did psychology undergraduate, I did clinical neuroscience. At no point did I do physics, did I do A-level maths, right? But I'm still a data scientist. Now, that's what kill set, it's actually skill set, but bear with me. What do you need to launch a data science career? Well, we can't get away from the fact you do need to have a solid understanding of statistics, of programming skills, of machine learning, of multivariable calculus, both linear and nonlinear algebra, visualization skills, and software engineering. And just like I said earlier, with a kind of Swiss Army knife, not everyone has all of these things, right? It's about, it'll make you cry, it's a bit like an onion, but it is about layering your experience and your learning to build up this arsenal. Okay, no one has it all, and I'm still working and will always be working on different areas of my capabilities. And in the last few moments, I just wanted to talk about if I kind of think about the right data role. You're probably nearing or thinking about kind of what do I do next? Do I want to go into data? And then you do a Google and everything is related to data. And how do you even start to choose what that looks like? What's the difference between a data analyst, an ML engineer, etc., etc.? And that's just what I want to finally touch on here. And the way I'm going to do that is just very briefly talk about a concept, which is, let's think about a hospital, okay? So a data engineer, their role is essentially to make data safe and consumable for analysis, okay? So they are making the data ready for data analytics professionals, okay? Data analysts then focus on things like reporting and summarize. How well is the hospital currently coping? How are discharges of patients going? Are there any blockages or bottlenecks? And letting the hospital know that at the right time, and interpreting that data. Now, in addition to that, what the data scientist is doing is saying, taking that historical information, what do I predict the number of patients will be in the hospital? Where do I predict the bottlenecks will be, let's say next week? And what are the prescriptive or best next actions to take? And so I just wanted to break that down in the last few moments of what does that look like from a skill set perspective. And I think what's really important, and I say this as a director of data science and engineering in a delivery team, is that they are all hugely complementary roles, but you have different leanings to different parts of that Swiss Army knife. So your data engineer is focused on software engineering, on big data, on database management, whether that be SQL, NoSQL, or graph, and machine learning deployability. I think I just made up that word, but basically the deployment of machine learning algorithms and data engineering. And the typical types of technologies they will be using are things like Spark, Scala, Docker, Kubernetes, things to containerize that machine learning algorithm in a cloud environment. Your data analyst will be really, really focused on the business and really focused on data visualization, understanding and wrangling that data to produce those reports for the business. And where the data scientist really kind of maximizes or looks to, from a skills level perspective, is obviously programming, machine learning modeling, needs a very deep understanding of statistics, data wrangling, and typically uses, as we saw earlier, Tensorflow, Scala, R, Python, Keras, and Spark. Now, I think I've just come to probably the end of my discussion with you today. Please do feel free to reach out to me. My marriage can only survive on social media platform. So I'm only on LinkedIn, but please do drop me a message, connect with me. Like, I love talking with people that are interested in technology or thinking about their careers, or just want to chat about that they saw a fish when it was actually a dog. Obviously, I work at KPMG. We have, sometimes it's a bit unknown, but a huge technology practice across a huge amount of public and private sector clients. So I, for example, work in a lot with our infrastructure, government and healthcare clients like the NHS. And we also have what we call IT's her future, or it's her future. See what we did there? Because we're very aware of diversity and increasing all forms of equality and diversity in technology. So please have a look at that. So I'm going to pause there and ask if you have any questions for me.
Seems like we're just getting an influx of thank yous, Rebecca, because clearly you blew them all away. Rebecca, I just want to add on, I thought it was really interesting about how you shared about your career journey and how people typically thinks the road to a data scientist and what it looks like, but then you're talking about, you know, your background in psychology and things like that. And I think it's really inspiring and empowering for anybody, especially because of the fact that I work in a university. So I understand that a student is from, you know, the 18-year-old all the way up to, you know, somebody who's got 25 years experience on me. So I think it's really great how you're able to share that knowledge as well. And your career trajectory to me has been more of, these are things that you found interesting and you wanted to ask the question why. So you went on that journey and jumped in with curiosity, which I think is really, really great and really inspiring, just in regards of what we have. So I was just trying to have a look here. No, they're still just all saying thank you. See, our speakers today, I have to say, all of our speakers have been on point, to the point where it's like nobody can even ask questions, because it's like anything that even I thought of asking throughout the presentation, at some point you turn around and answer it without somebody having to put their hand up. So it's really, really great. All of our speakers have been so prepared, and it's just been a wealth of amazing information. I've been truly inspired. I have to say, I've been truly inspired by all of the speakers that have come on today, especially with yourself, Rebecca. I think I have 2 questions there. I don't know if you can see them or if you want me to say them out today. So Emma Powderly wants to know, thanks so much. Just wondering, how difficult would it be to move between data engineer, analyst, and scientist?
As in across those 3 that we spoke about. So I love quotes, and I always live by like anything's possible, right? But joking aside, I think that it's about understanding what that role looks like, and hopefully, you'll get the slides and you can have a good old Google about kind of what those technologies are. And I don't think it's difficult to do that, as long as you have the passion and curiosity to move across. I think as well, where things like Coursera, cognitive AI, which is IBM's free offering. I know Microsoft are democratizing a lot of this technology. There are so many online ways to upskill. So I don't think it's difficult. I think it just takes time. And I think it's that's difficult. Finding the time is hard. And I don't think it's always equitable for everyone in society, because, some people have lots of reasons why they're working kind of 40, 50 hours because they're a single parent and they don't have time to upskill. And I think that's a much larger societal issue. But I'll get off my kind of rant now. But I think, as long as you have the time, there definitely are the abilities and capabilities out there to go find. And also have a look at Kaggle and those kind of online resources.
Thank you. Jack Bowes wants to know, I want to learn about how machine learning is used to model protein folding. Do you have any recommendations on resources I should use?
Resources you should use. So if I take a step back, we're probably, you've seen the recent announcement by DeepMind around protein folding. I think from a resourcing perspective, if the question, and again, we're sadly not in the same space, we're digitally aligned, but not in the same, so I can't ask you directly, but I think if you're asking what do you need to learn to be able to do those things, can I just ask, is that the question, or is it something different, just so that I don't go off on a tangent?
I'm waiting for him to write in. Do you know what we'll do, Rebecca? I was going to say, I'm going to wait for Jack to write in, just to ensure that we're hitting his question. I might go on to the next one just to give Jack a bit of a couple of minutes just to be able to type that in. So Cigarette 16, I'm so sorry if I'm saying that wrong. That's a great, insightful talk. Thanks so much, Rebecca. Hey, I was just wondering, would you at all differentiate between machine learning engineers and data engineers?
Yeah, and I think we're seeing very much the kind of rise of the machine learning engineer, and I think we may see in time data scientists having that very hybrid role. I kind of see the data engineering as more about how do you operationalize machine learning once built and trained across an organization. But I think they're blurring. I think there is as time goes on, an ever increasing Venn diagram that's going to merge there. So I think eventually that will be subsumed into one thing. I'm not sure that helps. That's my prediction as a data scientist. I'll be out of the job
I've
soon.
got Fanula Cahill. She wants to know, are there any open source data projects that you're enjoying at the moment? I'm always looking for cool new things to contribute to.
Yeah, so one thing that I'll talk about, that I'm able to talk about anyway. So we're working, our national charity, KPMG, is the NSPCC, and we're using things like topic modelling and natural language processing to understand the impact on children's mental health throughout the pandemic, and how that's changing, and how what they're talking about online has changed. And we're seeing some really difficult and hard messages for children and their mental health at the moment. So that's something that I'm very proud that we're supporting, and also working collaboratively with the NSPCC to hopefully enable some help for those children as well.
Rebecca. So Jack came back, and just to go back, his initial question was, I want to learn about how machine learning is used to model protein folding. Do you have any recommendation on resources I should use? And he came back to says, yes, what skills I need to learn, as well as a place to access existing machine learning models to learn from.
Yeah, great one. So I would say with protein folding, start to look at graph AI. It's a particular type of artificial intelligence, and also start to concentrate on reinforcement learning combined with back propagation, because that's actually what was the process that DeepMind looked at when they did the protein folding. So I think those three things, and that sounds really easy, right? They are massive research themes in and of themselves, but they would be, and places to go are things like MIT license, Stanford. They all have YouTube videos as well, and they're fantastic. And also DeepMind, they have a really good blog about how they do this as well, that's really accessible.
Perfect. I think that's all the questions, unless anybody else, our attendees, want to ask Rebecca anything before she runs off. She'll still be here though. She'll still be contributing, and I'm already looking for you on LinkedIn so I can
Yeah, do. Please do, because I think, I'm really passionate about this field, and also diversity and all the different forms of diversity. And I love when people reach out, and I will always make time for you, but it'll probably
that's
be
so amazing, Rebecca. Fionnuala just wants to add back in there. She says, wow, that sounds like an incredible project. Is it an open project that we can contribute to?
I don't think it is, because it's contractually between KPMG and the NSPCC, but I know that the NSPCC are always looking for technologists to help them. The gentleman's name is Matt Harper on LinkedIn, so please feel free to reach out to him, and I'm sure he'd love to hear from you.
And Jack just wanted to come back to say thank you very much for the insight in regards to answering this question.
No worries.
I think that's it, Rebecca. So guys, do connect with her on LinkedIn. She's already said, I'm holding you to it. She's going to say she's going to write us back. So me and Chloe are already fangirling over there, just waiting to get our connection request approved. So Rebecca, thank you so much for coming in, for all that knowledge. Pleasure. As well, for letting me fangirl and not embarrassing me even further. So thank you for that. You've been an excellent speaker this afternoon. I know the attendees obviously really appreciate you being here today. So thank you so much for the participation.
Okay, take care, everyone. Lovely to meet you. Bye.
Okay, guys, we have about 5 more minutes. So how about we do a little bit of refuel, hydration, because, skin, guys, it's cold outside. So we need to make sure that we're hydrating that skin. So if you guys, head off for about 5 minutes, and then we're going to come back at 3:30, where we will have Cassidy be kind of taken over. So like I say, guys, just take a little break, come back, stretch the legs. I don't know where you guys are sitting. So stretch your legs and let me know. Also, just so that you guys are aware on social media, do keep tweeting, do keep, hashtagging System 2021. Let us know about what your setups looks like. We seem to have gone from we were trending number 4 going up to it's number 3 now. So please keep sharing, keep going on. And Fiona, I hope that your internet provider allowed you to come back in to watch it. If not, at least you know that you got your own shout out from the host. So I do hope you're okay, and I hope you get to see the rest of the conference. Guys, I will be back with you I'm after talking too much, in 4 minutes, and then we can get back into it. Bye.